everyone, my name is Joshua and I'll be solving some Codesignal arcade problems. And the question that I'll be solving is sort by height. Alright, I was practicing a little bit because my insertion sort, um, my quicksort algorithm was failing, so I'm going to go rely on, actually let me just give you more context. This is the question I'm trying to solve. We have people standing in a row in a park, and there are trees that you cannot move, and they're noted by these -1 values. And we want to sort all the people in ascending order. So given this example right here, we cannot move the -1s, but we can move the other numbers. And when it's sorted, it should look like this: 150, 160, 170, 180, 190. And you can see here the constraints. It could be up to one array value, and the values can be -1 to whatever. It could be a high number. All right, so let's solve this one. So I tried doing a quick sort, and I'm having trouble doing quick sorts. So I'm going to do what I do best: insertion sorts. Now let's deal with the situation. If it's null, or if its length is equal to 0. These are some base cases that we need to think about. Or a dot length, equals 1, then return array. We don't really have to deal with it. But now, if it is not, if it's more than 1, then we have to deal with it. So let's go ahead and deal with it. So we start from the left, and we want to mark the right value also. All right. Now, while L is less than or equal to R, and it will continue trying to sort this whole array around so that we start from the end, from the start, and at the other point from the end, and then as it goes, as we sort the values and towards the middle, it means we're done sorting. That's the power of insertion sort. So let me think about this clearly. All right, so first, if we go to the first part of the array, and the L, like the pointer put for L is equal to -1, it means it's a tree. That means we can't do anything about it. So we increment that one up, and now we have a smaller range to deal with. So what I'm doing right now is this determines the window of what we'll be trying to sort. And since the L is starting from 150 to, starting at -1, and since it's a tree, we shorten that window to something smaller that we can handle. Now, something else to consider. Else, if the A of R is equal to -1, that's an indicator also that we need to shorten the window. All right, but if it's not -1 here and -1 on the other end, that is something that we can start sorting. So else, let's see here. Let's say we want to do an insertion sort. A, L, R. So after we do our insertion sort, what I'll be doing is that I'll take the L value to compare. Is there a value smaller than L in the rest of this array as it goes from the right end to the intro, to the start? And if there is, we switch it until we go through this whole array and we have the smallest value at the L value. And when we do that, we can shorten the range and we don't have to check the L value anymore. So this is something we have to consider. If we get the smallest value at L, we can shorten the window and try to find the shortest value with the remainder of the arrays, So now we have to go and question and find out how exactly can we perform this insertion sort. So we give it an int. It's going to be an array. I think keep it consistent. I just keep it as A, even though I prefer L. I mean, excuse me, if I prefer to use A here. I mean R, so you know that means array. I'm kind of tired today, guys. Whew. Trying to solve this problem took me like 5 hours. I just got bored. I could do better things with that one. But whatever, guys. I do it for you. Do it for you guys. Just give me the like and subscribe when you're done with this video. Alright, so when we do an insertion sort, I start from L. No, I'd start from the R because we're going to go backwards to find the smallest value. And end is greater than or equal to L, and end minus minus. So we're going backwards. And as we go backwards, if there's a value, but first, we have to do that consideration thing. If the A of L is equal to -1, oh wait, we can only do this if it's not equal to negative. We could start sorting it if it's not equal to -1, or A of R. Oh wait, A of L is staying the same, isn't it? Okay, then, well, it's really just A of end, isn't it? Yeah, I think it's just A of end that we have to think about. A of end does not equal -1, and also if A of L is less than A of end, then we could do some swapping. Oh no, A of end is less than that. So let's just put this here in a much easier way to read it. End is less than the L. We want to switch those values. So I'm going to create something called a swap. Swift array and end L. And now you might be wondering, what does it mean to do this swap? Let's define it here, private. I like doing some helper methods and keeping it kind of modular in a way because it makes it easier to understand what's going on in the code without making it too jumbly, spaghetti codey. I know people don't like saying spaghetti code, but deal with it. Alright, equals array P1. P1 equals, oh, sorry. P1 is going to equal whatever value was in AP2. So I'm doing the swap right here, guys. All right. Now what? What's the swapping? Oh, just swap right here. All right. And it should do it. Would this work? Oh my gosh, I don't know, guys. Oh, it worked. Nice. So let me submit this and see if it actually catches on. Nice. I'll explain what happened here in this code. So insert by height. If it reaches these base scenarios, if it's a null value or the length is 0 or 1, we could just return that array because no changes can be made anyways. But otherwise, we have this window we deal with, starting from the first to the last, and we sort of squeeze that window as we try to sort this whole thing out. If it's a -1 and A of L or A of R, we could ignore that because we cannot swap trees that are marked as denoted as -1. Otherwise, once we reach the point that we can start sorting it, we sort backwards. Like for example, we start from whatever the R value was, and if it reaches a point where it's smaller than whatever the L was, we swap it because we want the smallest value at L to make sure that it goes in ascending order at the end. Because we start incrementing and shortening that window, but we know that this one is already at the smallest, we could just go ahead and shorten the window left to right. All right, guys, this one was energy consuming, so hope this was helpful. If you have any questions, post it in the comments below. If you have a better solution, if you implement a quick sort, I'm going to give you a freaking high five from where I am, and I won't tell you where I am because it's a secret. As a matter of fact, maybe I'll tell you, it's in